All right, welcome back to Calc 2. So we're continuing on our tour of integral applications. And the big new idea for today is weighted average. This is going to combine some of our ideas from last time. We had a notion of average in the function. And we also had a notion of density, how you can integrate density to get total stuff. Turns out we can combine those ideas and have a notion of weighted average of a function with respect to a density. Okay. So, as a setup, let's think about the case with finitely many points. So I'm sure you've seen weighted average before in algebra or whatever, but let's sort of introduce some of the language here. Suppose I have some numbers, let's say W1 through Wn. They're all going to be non-negative, and they're going to add up to 1. The weighted average of a different set of numbers, so weighted average of, let's say, x1 through xn with weights w1 through wn, is just the sum of w1 x1 plus w2 x2 up through wn xn. So an example where weighted average is, of course, relevant to your life is your grade in this course is a weighted average. So if you look at the syllabus, you can see the weights. I don't have them by memory, but the final exam is, let's say, 30%. Maybe the quizzes are 25. Check the syllabus for actual numbers. So you take your grade on final exam times 0.3 plus your grade average on the quizzes times 0.25, add them all up. There's your grade in the class. Pretty familiar idea. Note, this generalizes ordinary average. If all the weights are equal, so if they're all equal to 1 over n, this is an ordinary average. Ordinary average where you add up the numbers and divide by n. This would be like x1 times 1 over n plus x2 times 1 over n. It's the same thing. So this generalizes the notion of average so that you can kind of make some terms more influential than others. We could define a notion of weighted average where these weights don't add up to 1. Okay, so I'll call this unnormalized weighted average. This is maybe more lingo than it's worth. Suppose I have some numbers, and I'm still going to require them to be positive, but they maybe don't add up to 1. So maybe my weights are 2, 3, and 5. Suppose I have 3 numbers and I want to add them up and I want to sort of weight them by 2, 3, and 5, meaning in a proportional way. So, this one is 2/5 as important as that one. How can I do that without this criterion that they add up to 1? What kind of expression could I write down so that x1, x2, and x3 would be sort of weighted proportionally to my numbers?
Multiply it by the value that you're
that you're weighted as. So, suppose my weights are 2, 3, and 5. I take 2 times x1 plus 3 times x2 plus 5 times x3. That could be too big to really make much sense as an average. Maybe that's just a lot bigger than any of them. But if I divide through by the sum of the weights, then this starts to make sense. Right? If I took 2 over 10, 3 over 10, and 5 over 10 as my weights, then it sort of takes care of things. Basically, if I have some weights that don't add up to 1, I can normalize them. I'm really taking this weight and this weight and this weight in an actual weighted average. I'm just dividing them all by the same constant, so that it keeps the proportions right. All right, so we could consider this is the weighted average. With respect to these weights. All right, so if they aren't already normalized, like in this definition, you just divide through by this. Okay, well that's all just mathy. Let's look at a couple of places where this comes up. One of them is the notion of center of mass, which is a physicsy thing. So if I have more than one mass, I can define the center of mass of several point masses. So we're going to look at centers of mass in one dimension. We have some limited ability to break out of our one-dimensional world, but let's start with one dimension. What that means is I have some line, and along the line I have placed several masses. And they could be bigger or smaller than each other. So let's say M1, M2, and M3 are the masses, and they're located at different x coordinates. This might be at coordinate x3, coordinate x2, and coordinate x1. Okay, I'm going to assume that coordinatize my line as the x-axis. So, given point masses, this is an idealized assumption. I'm assuming my masses take up no space. Right? They're sort of like atoms, but even smaller. Right? They're localized to be infinitely small. Given point masses, with mass m1 through mn, located at coordinates x1 through xn, the center of mass is, this should look pretty familiar, m1 x1 up through mn xn divided by the sum of the masses. In other words, the center of mass is the weighted average of the x-coordinates of all those points, i.e. the center of mass is the weighted average of the coordinates, weighted by weight, mass. We'll use the notation x bar. Bar is sometimes used for average, so this is like the average x, or weighted average x, is this that expression there. All right, so we're giving the bigger masses more influence. This mass is 10 times as big as this. The center of mass is going to be closer to there. Good. All right, so I'm not going to bother going through, oh, sorry, that was going too quick. Sorry. I'm not going to bother going through an example with numbers, but it just is a weighted average. So let's talk about why anybody cares. We get some sense of this already. What does this tell you that might possibly be useful for anything? Gary?
Designing a bridge, for example, or building.
Yeah, so how do you use the center of mass calculation for that?
Maybe if you're creating like a foundation for like a parking garage with steel beams,
Yep.
Concrete, and how that distributes the weight of like having a bunch of cars parked on it, that might make a big difference.
Right. Well, and one of the things that, yeah, so if you want to analyze like how much stress is on a given beam or something, you might want to know where's the center of mass. Is it like over that beam or is it way off somewhere else? Yeah, I hadn't even thought of that. So some uses include analyzing stress on materials due to weight. So you want to know how much gravity is sort of straining your concrete or steel or whatever. You want to know where your center of mass is. On the, yeah, Luke.
Shipping, like loading a tanker, how like all those little science museums, they have a thing where you stack the boxes on one side of the boat and it goes over. You have to balance them out.
Right, right. Whether something tips, I'll just call this tippiness. And you may have learned this at age 2 or something, playing with your blocks. If something has a high center of mass, it's likely to be tippy, right? So if I take a little stick, a big weight on top, it might fall over. Slash stability. Going back to that parking garage, if you designed a really bad parking garage where there was a lot of weight over here, that doesn't look like a good design to me. So you drive up the ramp and then there's nothing supporting this. Okay, that's going to be a problem. That's related to center of mass. The one-dimensional version, you can think of teeter-totter, right? Here's a place where center of mass comes up. Let's suppose you're out on the playground with your younger sibling, and you want to be able to have a reasonable game. Seesaw with them, they're smaller than you. Well, that's not going to go so well. But maybe that will. If the fulcrum is near the center of mass, if the fulcrum is exactly on the center of mass, you can sit there in equilibrium. That's the balance point. And we can think of that over here. Imagine that I have a rod that has no mass of its own, up to an approximation. And I have a bunch of masses that are attached to it. Right? So, thin, relatively light, but very sturdy wire or rod or something with mass. I want to put a fulcrum somewhere. To balance it, I'm going to put it at the center of mass. The reason behind it has to do with the formulas for torque, which is a whole bundle of fun that I won't get into at the moment. So that's an application. Another important application is if you're analyzing the motion of several particles, it turns out a very powerful idea is break this into two parts. First of all, can we track how the center of mass moves for this system? And secondly, can we figure out how each of the objects moves with respect to the center of mass? And separate out into those two problems. So if I have, an object that I throw through the air, let's say I take my calculus book, and for some reason, it's not been a good day, and I'm going to throw my book. It's going to sort of tumble and rotate and do all this weird stuff. If I was trying to, I'm not going to do a demo, because I didn't. That's fine. If I was going to analyze that motion, it's pretty complicated to track a 3D body as it rotates and flies through space. But if I were going to analyze it, I would analyze it in two parts. First of all, how is the center of the mass of the book moving? And it's probably just a nice, simple trajectory, like you get from throwing a point mass, classic ballistic motion. Secondly, right, with regard to the center of mass, it's just sort of sitting still and rotating. Can I analyze that? If I wanted to get my foot in the door with figuring out that motion, that's how I would do it. The most famous instance of this is if you're figuring out how two objects orbit, say the Earth and the Moon, and they're both moving through space while rotating around each other. That's pretty complicated. It turns out the key is to say, okay, what's the center of mass doing of the Earth-Moon system? That's just going around the sun. Secondly, what are each of them doing with regards to the center of mass? And once you write down the equations that way, the problem becomes solvable. All right, so most of that has nothing to do with this course directly. That's just kind of for your edification, general cultural knowledge about centers of mass. We're going to be concerned with how to calculate them, and in particular, how to calculate them when the number of masses goes to infinity. That's kind of a theme for many of these applications. Suppose I don't have three discrete point masses. Suppose I have mass that's spread over space. We had problems like that last time. If I have a density function, I can find the total mass. Okay, suppose I have a density function, can I find the center of mass? Related question. And thinking ahead to the midterm, natural part A, part B of a two-part problem, right? Here's a density function. Part A, how much total mass is in this rod? Part B, where is the center of mass? All right, so suppose rather than discrete masses, especially point masses, I have mass spread over space, over one-dimensional space, according to some density function. Say rho of s. How to find the center of mass? And let's say for x between A and B, so I have some segment on my axis where the mass is. All right, so let's come at this with Riemann sums. We're going to get out our calculus chopper and slice up the line. And then we're going to use the center of mass formula for finite masses. And then we're going to take a limit as we chop finer and finer. Right? Sound familiar? Okay, that's how all this stuff works. So I've got my axis here going from A to B. So I've got my one-dimensional rod here with this density function. From last time, I know that the total mass, let's call that capital M, is the integral from A to B of the density function. So if I don't already have that information, that's probably the first thing I'm going to find. Total mass of the rod. Maybe that was part of the problem anyway. All right. All right, so suppose I chop into segments of width delta x. All right, so chop, 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 chop. This is delta x. So I want to know two things about each of those segments. First of all, what's its mass? And secondly, what's its coordinate? Where is it? Well, its coordinate is just x. The mass of each segment is approximately, we'll call this delta m for a little bit of mass, right? A little bit of mass, it's basically density times delta x. Actually, that's the same analysis that we had last time. I'm going to approximate the density as being basically constant over a tiny little interval. So for that tiny little interval, I can just take density times length, the way you do for constant density, and that's basically the mass of this teeny little chunk. Okay, so I know how much mass this little bit is. The mass is delta m for that little bit. And this little bit has a different delta m, delta m, delta m. I'm using the same symbol delta m for all these little bits. If I were doing a proper Riemann sum, it would be like delta m sub k, but then it gets cluttered. So I'm just going to call that delta m. All right, so I'm going to add, well, wait, no, I'm not going to add them up. All right, so the center of mass, x bar, is approximately, all right, well, suppose I had a finite number of masses. I'm going to approximate my situation by saying I have point mass, point mass, point mass, point mass, point mass, and I'm taking their center of mass. Well, I'm going to add up my x coordinates times my little bits of mass. Right? It's like x1, m1, x2, m2, x3, m3. I'm adding up x times a little bit of mass, and then I have to divide by the total mass. This is that unnormalized weighted average. Right? It's like where I want my weights to be 2, 3, and 5. I've got to divide everything by 10. This gives me the approximate center of mass, right? Approximate because the slicing is, is an approximation. All right, well that's delta m is that. That's the sum of x, rho of x, delta x, divided by little s. So when I take a limit, that's just going to become an integral. Taking a limit, my exact center of mass is going to be the integral of x times my density function divided by my total mass. And if I want, I can also expand that this way. X times the density divided by just integrating the density. All right, so this is how you do centers of mass. Let's do an example. See, last time we had a sine of pi x density function or something like that, right? All right, so say my density is sine of pi x, where x runs from 0 to 1. And let's find the center of mass. Okay, so last time, we found the total mass. So the integral from 0 to 1 of sine of pi x dx, and that was 2 over pi. Okay, so if we hadn't already done that, we could just do that calculation, no problem. So x bar, I'm going to pull this 1 over m out front of the integral. X bar is 1 over m integral from a to b of x rho of x dx. That's my center of mass formula. So 1 over m is going to be pi over 2. And then I'm going to integrate from 0 to 1 x times the sine of pi x dx. Well, it looks like between this and the last quiz, integration by parts has made a big comeback in the last few days. We haven't done as much of it recently, but it's going to be on the midterm for sure. I've got a product of two functions, and I know how to differentiate one and integrate the other so that this gets nicer when I take its derivative. I could use my I8 acronym, all that good stuff. Let's call this U, and this dV. So the derivative of x is 1, that means du is dx. And the integral of sine, actually we did that last time on the way defining mass. The integral of sine is negative 1 over pi times the cosine of pi x. Now if I didn't see that, I could do a u sub to help find my way there. So I need to use integration by parts. Before I erase this, say integration by parts happens a lot with centers of mass, because even just look at the abstract form. Right? This is almost begging to be u and dv, because I can differentiate this to 1. It's a very common way to do a center of mass problem. Okay, so I still have my pi halves. So u v is x times negative 1 over pi x sine of pi x evaluated from 0 to 1. Cancel the pi's there. Minus, still carrying around that pi halves out front, integral 0 to 1 of v du, that's a minus 1 over pi cosine of pi x dx. Cancel those parts as well. Okay, so I'll just carry this around unevaluated for now. So negative a half x pi x from 0 to 1 plus, all right, so if I want to integrate the cosine, I can do another 1 over pi times the sine. So that's now 1 over 2 pi sine of pi x. And again, if you don't see the antiderivative of cos pi x immediately, then you do a u sub. This is going from 0 to 1. All right, I'm going to combine these, so it's this whole expression from 0 to 1. So evaluated at 1 minus evaluated at 0. This should be a cosine, shouldn't it? cosine. My v was, I'm having a hard time reading my own red chalk. V was a negative 1 over pi cosine. The sine of pi and the sine of 0 are both 0. So this term actually is just going to die over there. So at 1, I have negative a half times 1 times the cosine of pi, which is negative 1. And if I add this in, I have the sine of pi, which is 0. Evaluating at 0, the cosine is non-zero, but it gets killed by this term. And this is 0, 0. So when the dust settles, it looks like I have a half. All right. Before I move on from this example, I want to explain why you probably could have guessed this. All right, so 0 to 1, my density function is the sine of pi x. Now the sine, if I go from 0 to pi, goes through half of its cycle, goes up and then down. This is sine of x. If I take the sine of pi x, it just compresses this whole thing so that it goes through its cycle pi times as fast. The density is symmetric. So, of course, the center of mass is in the middle, right? It's sort of evenly weighted to left and right at that middle point. So, that kind of reasoning works. Like centers of mass do respect that kind of symmetry. And in certain special cases, you could see that. You could just find the center of mass by inspection if you notice that. But in general, you have to do the integral. Okay. So one of the fascinating connections in this sections is the fact that center of mass turned out to be exactly the same calculus as something that looks very different, and that's the expected value of probability. All right, so I'll introduce expected value with an example. Let's play a game. Roll a die, and if you roll 6, I'll pay you $4. If not, you pay me $1. Would you play this game? Doesn't seem very smart, right? Clearly you're going to lose money. Because a sixth of the time, 5/6 of the time you're paying me $1, and 1/6 of the time I'm paying you $4. That's not a good setup for you. So, especially if you play this game repeatedly. If you're going to play this game once, okay, fine. But if we're going to play this game 1,000 times, I'm basically guaranteed to take your money. That's how casinos win. They have many, 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 many games, and it averages out statistically. All right, so the way that we would analyze this by using sort of the math of probability theory is we'd say, all right, let's let X be your winnings. And there are two possible values that your winnings can take. So in the lingo from last time, which isn't so important for this course, this is a discrete random variable. It takes on two possible values. First of all, you could be winning $4 with probability P1 equals a sixth. That's how likely you are to win those $4. The second possibility is -1. You could be losing $1 with probability P2 equals 5/6. Okay, those are the two possible outcomes, each with their own probability. We'll define the expected value I'll use this notation E of x, and that's not as big a deal as the idea. E of x is P1 x1 plus P2 x2. So in the case of this game, there's a 1/6 chance that you'll win $4. So we're going to add that together with the 5/6 chance that you'll lose $1. And this tells me that your expected winnings from this game are negative $1/6 of a dollar. All right. So what does that mean? Expected. Will you expect that if you play this game once, you're going to lose $1/6 of a dollar? Well, actually, that's impossible. Right? This game has integer payouts. It's not the case that if you play this game once, you're going to lose $1/6 of a dollar. I guarantee you're not going to. So what does this number tell you?
In the long run, you'll lose $1/6 of a dollar for every roll you do.
Yeah, so the best way to understand this is a long-term average. Right, so the meaning is a long-term average. If you were to play this game n times, right, or large n, your winnings from playing n times are going to be approximately negative $1/6 n with high probability. And there are some technical statements of that, the law of large numbers, and even more fascinatingly, the central limit theorem. Make this statement precise. The law of large numbers, it has to do with a kind of limit. The limit is n goes to infinity of a certain probability. Basically, the probability of being significantly far away from this goes to 0 as n goes to infinity. So your probability of beating the house goes to 0 as you play more and more time. In even more detail, if I look at the probability density function of playing this n times, it's a bell curve, and the center of that bell curve is negative 1/6. And the bell curve gets tighter and tighter as n gets bigger and bigger. So it starts to look almost like a vertical spike. There's almost no chance of being significantly far off from that expected value. So as n goes to infinity, your bell curve shrinks and shrinks and shrinks. But it shrinks around this common average. So anyway, all that's fascinating, very important in the real world. See Math 370 for the full story. For our purposes, we're going to look at how do you calculate this? How do you find an expected value? So if you have finitely many possible outcomes, you do this, and what does this remind you of from earlier today? Well, I guess it's the topic of the whole day. It's a weighted average. In fact, one of the things about probabilities is they're all positive, and they have to add up to 1. The probability of 1, something happens. Well, our first definition of weighted average was saying we have these numbers W1 through Wn that are all positive and add up to 1. That's exactly what probabilities have to do. So the probabilities are the weights. We're going to take the possible outcomes weighted by probability. That weighted average is the expected value. Okay, well, what if we have infinitely many possible outcomes? We saw an example of this last time or the time before when we integrated a probability density function. What if we have infinitely many possible outcomes? We could run through exactly the same analysis with centers of mass. It turns out that expected value is to probability what center of mass is to mass. So what if we have a continuum of possible outcomes with some probability density function let's see, call it, I don't know, P of X. Well, center of mass was a weighted average that we took n to infinity. Expected value is a weighted average where we take n to infinity. It's exactly the same math. So the expected value of my random variable ends up being the integral of x times the probability density from A to B. And here, I don't have to divide by a total mass because the thing about probability density is it's already normalized. It already has total probability of 1. So I think this is a fascinating case where exactly the same math is two very different things, right? Point masses, probabilities, same integral. Let's do an example going back to whether my car is going to die. Suppose P of t equals, let's see, what is it, 1 over 10 times 1, this is weird normalization constant up here, e to the minus t10, and last time, is the probability density function for my car breaking down. I want to find the expected value of when my car breaks down. Okay, what's the expected time to break down? Now, going back to discussion about the meaning of expected value, if I figure out the expected value is 6 years, that doesn't mean I have a lot of confidence that my car is going to die exactly on year 6. What it means is if there are 1 million people with cars exactly like mine, and you average out how long all of their cars will last, it's going to average out to about that. And so this is kind of an actuarial calculation. But for me individually, it's not going to tell me that much. All right, so let's see what would happen. So the expected value of my car breaking down, let's say I use t, not that that matters, is the integral. I had t up to 40. That's, again, carrying over from last time. And assume my car dies in the next 40 years. Integrating from 0 to 40, but this weird normalization factor, times x, or in this case t, times my probability density. So, all right, we might just have time to do that integral. Yep. So I'm going to substitute. Let's say u equals t over 10. So du is 1 over 10 dt. And I happen to see that 1 over 10 here on dt. So keep this out here. T is 10u. This is e to the negative u. Actually, I'm going to call it w for reasons that will become quickly apparent. and dw. And if t goes from 0 to 40, dividing by 10, I'm now going from 0 to 4. All right, well, the reason I changed my letters in the middle was, wouldn't you know it, I'm about to integrate by parts again. U dv. So v is negative e to the negative w dw. So you integrate that negative exponential there. So uv, that's negative, keeping track of these constants here, negative 10 w e to the minus w, evaluated from 0 to 4, minus the integral of v minus e to the minus w du, again with this constant call out here. All right, so what do I have here? Here, again, I get a minus, so I'm going to put these terms together. I have a minus w e to the minus w, and then another minus e to the minus w. I'm going from 0 to 4. Right, so evaluating at 4, I have 5 e to the minus 4, and then evaluating at 0, I have 1. All right, second straight time I forgot to bring a calculator. Let's see if I have this one in my notes. Anybody want to crunch that out? Actually, wait, here it is. It's about 9.25. So,
Couldn't you cancel them?
not quite like this with that. No, because it has a 5 and that doesn't.
Oh, okay.
Yeah, if you could pull out a 5 as a common factor, yeah, so if this were a 5, it'd be good. All right, so at least according to this, about 9-ish years until my car breaks down. All right, so be ready for centers of mass and expected value. 2 for the price of 1, though, right? You don't have to memorize 2 totally different formulas. It's all the same idea. It's all the weighted average. Monday we'll have a little bit more applications. Tuesday I'll probably set aside to just study for the midterm and kind of review where we've been. There's been a lot of things that have happened. And Wednesday's the exam.